Hi, my name is Bruno and I'm a technical educator at the Web3 Foundation. And today we're going to dive into Substrate, the framework for building blockchains that Polkadot and Kusama are both built on, and that actually a lot of parachains, the chains that will connect to Polkadot and Kusama, will also be built on. We'll explain Substrate, we'll go through some basic usage, we'll actually go through a tutorial, and you will power up your own blockchain very easily. And within an hour, we'll have a custom-built blockchain with a custom UI and custom functionality. And if there's time, we will also issue a magical forkless upgrade. And that's a type of upgrade to the blockchain itself, which can happen while the blockchain is still running. And that's really exciting in terms of what substrate-based chains can do. I hope that you're getting into this workshop with some prerequisites installed. I will share. I hope the organizers have shared shared a link with you for. Actually, let's cut that out. The organizers have shared a link with you for preparing for this workshop, and that link will help you set up everything on your machine to get this to work. So this includes installing Rust, and because Substrate is built in the Rust language, and building the entire environment needed to recompile and build your blockchain locally on your machine. It's quite a time-consuming process, and that's why that part is outside of this workshop, and that's why I hope you've done it all before diving into this workshop, because you will be able to follow along as you're watching this. So with that out of the way, let's dive in and see what we've got here today. So this is going to be a workshop for getting started with Substrate. And as I said, I'm Bruno. I'm a technical educator at the Web3 Foundation. My job is to demystify the technology that we are building there and that we are researching there, and to present it to developers and non-developers around the world to get them interested in our ecosystem. You can always find me on Twitter and Telegram or LinkedIn or whatever you want, or just email me, bruno@web3.foundation, if you have any questions about this presentation or anything else regarding Polkadot, Kusama, Substrate, our whole ecosystem, anything at all. I'm always at your disposal to answer any questions. So at Polkadot, we believe in a decentralized and fair internet where users control their own data. Where users also control their own identity and their destiny. And to do this, we need a free, open, decentralized, and censorship-resistant Web 3.0. And to do that, we are building a suite of blockchains in a way which will let other blockchains connect to each other. Now, in order to, this is the link that I mentioned in the intro, but if you haven't gotten through it, please go to bit.ly/polkaprep. This will prepare your entire environment on your computer to compile and build these tools that we'll be playing with. So in our mission to decentralize the web, we've built this Polkadot blockchain, which allows other blockchains to connect to it and to talk to each other through it. There are quite a few projects that claim to do the same thing out there today. The difference in this case is that Polkadot's connected chains share their security, where in other shared blockchain systems, you may have a problem of the whole ecosystem being only as strong as the weakest chain. Because imagine for a second, if the weak chain sent a message to a more secure chain, and that message includes something like increase that user's balance by 1 million coins. If that weaker chain then gets hacked or reverted or forked or something, what happens to the more expensive chain? Well, that chain is in trouble, right? Because it doesn't know which version of the past to trust. And so that makes the whole system only as secure as that weak chain. In Polkadot, every chain that connects to the ecosystem is as strong as every other chain. This is possible because they're all connecting to the relay chain, which is the master chain coordinating everything between the master chain. The relay chain has these validators, and the validators are validating random connected chains at random periods and giving them finality. So the chains that are connected to Polkadot, they get their finality. They produce their own blocks, but they kind of seal those blocks into finality through the help of the validators on the relay chain. So the entire system is only as secure as every other chain. And the more chains are connected, the more secure the system is. The more validators there are, the more secure the system is. But this sounds really complicated, right? How are all of these chains connected to each other, and how is this relay chain built at all? Well, this is built by the development company Parity from Berlin, which has built plenty of blockchains for enterprise users and other use cases before. And they realized at some point that they were repeating a lot of the work that they were doing. They were constantly reinventing the database, the networking, the consensus layer, the transaction queue, and a lot of these other things that blockchains typically need. So they decided, why not abstract all this, and why not just turn the knowledge that we have into a framework? Why not build a common starting ground from which we will build all of our future blockchains? We'll do that really well. We'll improve that. We'll let it out into the open for others to build on as well. And we'll have a really solid base so that people who are building blockchains don't have to spend 2 years researching and doing who knows what kind of research and development. Rather, they get this database, they get the consensus, they get the common pieces, and they can focus on their application logic right off the bat. And that's really powerful, right? So Substrate came to be from this idea. And Substrate is an open source, modular, and extensible framework for building blockchains. That's all there is to it. It's just like a template for building blockchains. Think of it as your blockchain's bootstrap. So Substrate provides the core things that I just mentioned. So that's the database layer, that's the networking layer, the consensus engine, the transaction queue, and a library of runtime modules, which we'll go through next. And each of these modules can be extended and customized to your liking. So you can be as specific in your application logic as you want. Your chain can be as application specific as you want it to be. And one of the key selling points of Substrate is its runtime. The runtime is composed of these different palettes, and these palettes are part of this system called Frame. These palettes are Rust modules that have certain functionality, but that functionality is encapsulated in that palette. It doesn't leak elsewhere. So it's all very Lego blocky. You can connect all of these functionalities together into one common runtime that then makes sense and is useful for you and for your blockchain. So how does that work? Well, for example, you can see up here in the circle, that's one runtime, right? And that runtime contains the palettes system, babe, pseudo, grandpa, indices, timestamp, balances. These are all different palettes, and they're marked with the pink border in the table below. But there are many other palettes as well, and these are not all of them. These are just some of them. But for example, if you want smart contracts in your chain, you would add the contract palette in there, and then you would rebuild. And when this recompiles, the new binary will contain the smart contract functionality. Your chain will automatically have smart contracts built in. So why is this special? This is just adding features, right? Well, it's special because of WebAssembly. And WebAssembly is something is like this binary code format which takes up very little disk space and very little memory. And the advantage of this is that it can be executed in a wide variety of environments, even the browser. Why is this important? Well, because this runtime, when we build it, when we compile this circle of things, it results in a WASM blob, a WASM file, a WebAssembly file. And that file has, along with the native file, along with the binary that you get from compiling the Rust, so you get a program that you can run, that contains the runtime. But along with that, you get this WASM file that also contains the runtime logic. And this WASM file contains all the logic that a blockchain needs to progress from one block to the other. So this contains all of the rules that the blockchain needs to be built, to continue building itself. And Substrate-based chains all have this common functionality. They will all produce this WASM blob. And this WASM blob is stored on the blockchain itself. So why is this important? Well, previously, whenever you needed to upgrade a chain, like for example in Ethereum, if you wanted to change some opcodes or something at the core level that would change the gas mechanics, if you wanted to add new crypto primitives into the chain or something, you would have to hard fork, right? you would have to develop this functionality, add it into the clients that are out there, and then you would have to get everybody who's running a node, who's running an Ethereum client, to upgrade that client to the new version. And everybody who didn't upgrade would be left behind on an outdated fork, which is no longer the canonical fork. You would have to get in touch somehow with everybody who's running your node, which is difficult in a system where most people who run your nodes are anonymous. And they would have to be aware or actively pursue updates and be aware of changes that are coming so that they can jump in and do this on their own. And that's an arduous and frustrating process for any hard fork coordinator, especially in a world where we are still communicating through centralized media about upgrading decentralized technology, right? That means that anybody who would just stop, if Google decides to no more like discussions about this, it's very difficult to reach those people. And we have like maybe one or two platforms through which we communicate. That's GitHub, that's Twitter, and that's maybe Google. And we rely on these platforms to communicate to everybody. Obviously, that's not sustainable long term. If you look at it from a kind of an absolutist kind of view, like we want to decentralize to the maximum. So what substrate-based chains allow you to do is they store this WASM blob on the chain itself. That's like maybe a couple hundred kilobytes. And it contains all of the logic. And now, when you're running a substrate-based client, so a node of a substrate-based chain, any chain, that node is reading data from the chain. And it also reads in that WASM blob that's on the chain. And it looks at the version of the runtime that's written inside that WASM blob. And it compares it with the version that it has locally in its own native code, in its binary. If those versions are the same, it will run the native code, the binary, because the binary is always faster than WASM. WASM needs to be interpreted, executed, and so on. So it's orders of magnitude faster to run this locally, like bare metal in the native Rust code. But if the WASM code's version is newer, then the client will use that. It will download that new WASM code that's on the chain, and it will treat that as the canonical runtime that it's supposed to execute. And while it will be slower to run, it'll use a little bit more resources of your computer, your node will actually upgrade itself. So if you replace that WASM blob on chain, that chain will upgrade itself while it is still running without you actually having to tell anybody to install a new node, to download new software, to replace their software that's running, and so on. This is extremely powerful. You basically get forkless upgrades. You basically get the ability to upgrade a blockchain with new functionality without having to talk to a single person except those in charge of changing that WASM blob. Now, how that change occurs, there are two different ways. One is through the sudo module, and you can see it here in this runtime. The sudo module is included. Now, the sudo module is just like an admin module that lets you execute any function of the chain at any time from one single key. So that's like an admin key to the chain. And this is often useful when a chain is just launching, so that you can do fast incremental upgrades without having to go through on-chain governance to vote for these changes, right? So with sudo, you can just replace that code and it'll go into effect immediately. The other way, which is the decentralized way, which you deploy after you're done with sudo, and after you're fairly certain that all of the kinks have been ironed out, is the on-chain governance way. And the way you do this is every token holder of every substrate-based chain has the right to vote on decisions that we call referenda. And these referenda can be anything from changing a simple value of the chain, like the maximum number of validators who are allowed to validate, to the complete replacement of the WASM blob for the runtime. So when I have some new functionality that I want to deploy into a chain, say for example, Polkadot is running right now. And right now in Polkadot, you cannot transfer dots, the native tokens. That's by design, because there's still the sudo module. The chain is still in like early launch phase, and during this phase, we definitely do not want to enable people to speculate with tokens. We don't want to endanger any economics of anything of the chain. And so the transfer functionality is disabled for good until the community enables it. And the community alone can enable it. The pseudo module will be removed and replaced by the democracy module very soon. And what's going to happen is the community, every dot holder, will be able to trigger the function, the runtime change, to allow balances to occur, to allow balance transfers to occur. And when they propose this, other people will be able to vote on this decision. And there are some mechanics on how to prevent plutocracy and how to make sure that the election is fair and how to make sure that the voting is, both and Sybil resistant and bribe resistant and so on. So that's a topic for another time. But the democracy is fairly fleshed out. We've been running this on a sister chain called Kusama for 8 months now, and it's worked fairly well. We have made over 100 runtime upgrades already and many different other types of upgrades, and the chain is progressing very nicely. So it's like an early release of Polkadot that's existed for 8 months now. So that it's verified to be working. But what matters here is that this forkless upgrade mechanism is available to every single Substrate chain. Every single blockchain that builds on Substrate has this ability to make an upgrade to itself without having to hard fork. You can, of course, hard fork. That's always an option, but you don't have to. You can avoid that nightmare of coordination now by executing these updates on chain. So what happens when the node takes the new WASM blob from the chain? It loads it in, it starts running it, and then it's up to the node operator, to the one running this client, the software, to upgrade when they feel like upgrading. They don't have to do it, they can do it, they can do it whenever they want. The only thing that's in it for them if they do is a bit better performance, right? The node will run native code because when they upgrade the client, the versions of the runtime will again match, and the client will no longer run the WASM blob, it will run the code that's native. So the native code will be equal to the code in the WASM, and the client will be running the code natively in a much faster way. So some performance to be gained there. This is important for validators, but for barely anyone else. So if a validator cares about performance, and they should, then they will of course keep track on the updates that are coming out and upgrade nodes whenever they feel safe about upgrading, like maybe wait a day or two after release to see if everything's fine and so on, and then upgrade as soon as they can, because not upgrading can make them slower than other validators, and then they might lose out on some rewards, right? But that's basically why they would want to do it. So in this workshop, what we're going to do is we're going to play with the Substrate node template, and the node template is a working Substrate node. It's like a very basic chain prepared for your experiments, and it's actually what most blockchains start out with when they're building their blockchain. So most of them start out with this and then build custom functionality on top of this. This is like the base starter kit. So Substrate is the framework that enabled the node template, right? Substrate is just a set of code that allows this to happen. So the node template is something you modify and turn into something you want. So we will have the pseudo module in here. So we will be able to execute administrative functions through an unlocked and very rich account that will be that will summon through the dev flag. So we'll run a development chain which will have this account unlocked. And we are also going to build a custom palette for this chain, so a custom module that will allow us to do some very application-specific logic, so that you can see how easy it is to customize a blockchain that you built on Substrate. We will also be using Polkadot.js apps, and that's a official front end for interacting with Substrate-based chains. The beauty of Substrate-based chains is also that because of the way they're built, because of this framework, every Substrate-based chain exposes a bunch of metadata from its runtime. And this metadata is available to any client that connects to that node. And this metadata will contain information on all the events, all the errors, all the functions, every single thing that the chain can do, all the constants. Everything will be in this metadata, ready for consumption by any connecting client. And this is kind of like if you're familiar with Ethereum and there's smart contracts and you have the ABI. So the ABI is like an interface, a JSON file, a JavaScript file, a JavaScript object file, which just defines which functions and values exist in this smart contract. And this is similar. So a Substrate node will expose this metadata about itself, and a UI will be able to customize itself based on this metadata. And polkadot.js.org/apps is one such UI. So this UI is generic. It lets you access any Substrate-based chain, and it will modify itself according to the modules that this chain has. For example, if you visit Polkadot through this chain, you will see all the regular functionality in there. But if you switch the connection to Edgeware, which is a smart contract chain based on Substrate, you will get a different layout, a different color, and the menus will now contain the option contracts, where you will be able to interact with smart contracts, which is not present in Polkadot or in Kusama when you connect to those. So the UI can self-modify based on the metadata that is being fed to it from the chain itself. And that's really powerful as well, because it lets you build generic wallets for all Substrate chains, right? And imagine how powerful that is. So we'll also be dealing with the Substrate frontend template. Now, Polkadot.js org apps is a behemoth, right? It's a big application suite that contains every single possible function, like in a simple button format. It literally contains, it's for power users, basically. It contains everything you can do to interact with a Polkadot, with a Substrate-based chain. And it's too much for everyday users. That's why we have, and it's also very heavy to build. It results in a huge website that uses a lot of memory and so on. That's why we have the Substrate frontend template, which is a lightweight React-based template that lets you interact also with any Substrate-based chain, but in a very primitive manner. This is something like it's going to look there. So we'll get a bunch of unlocked accounts. We will see our blocks. We will see our balances, and we'll be able to interact with different palettes inside of our runtime, as you'll see. Now, what's important to know when developing palettes and when customizing Substrate-based chains, we will be making heavy use of macros. And macros are like magic, magical code that expands into more code. So macros let you write very little code that becomes much more code during compilation. For example, if I make a macro that lets me type the number 2 and then plus and then maybe the asterisk button and then the number 7. During compilation, that macro could expand that little symbol to mean that the number 2 pluses itself, like 2 plus 2 plus 2 plus 2, 7 times, right? Stupid example, but that's how this code expansion macros works. And so we'll be using 4 main macros that everybody uses when they expand Substrate-based chains and the node template into their own application chain. Those are declare storage, declare module, declare errors, and declare event. Declare storage is used to tell the chain how you want to save your data. That's it. It just tells the chain which prefix to use in the data tree and how to fetch that data, how to save it. The declare module is like the main body of the palette. It's like the main part. Inside it, you will put all your functions and various other declarations that go, it's just the meat of it, it's the logic. Declare event will list all of the events your palette can emit. And an event is like if you send a balance to somebody, excuse me, if you send a balance to somebody, the transfer event is emitted. And anybody who's reading data from the chain can listen for events instead of reading the blocks and parsing the data inside the blocks. And declare error does the same thing for errors. Any error you can encounter while using your palette will be documented in declare error. So we can actually yeah, so the basics of runtime development in Rust here. It's important to note that in substrate-based chains in general, there's no such thing as a rejected and reverted transaction. So transactions always leave an effect on the chain, and they will always charge a fee for doing anything, even when a transaction is invalid. So if, for example, you have one dot and you try to send one dot, it's going to reject that sending because you didn't leave enough room to pay for the fee. But it's still going to charge you the fee for the attempt, because it has to leave a mark on the chain that you tried this and that it failed. Whenever you issue a command to the blockchain, you submit what's called an extrinsic. And an extrinsic is just like an outside input into the chain. And this chain will make a log of this attempt. And all of the extrinsics, failed or successful, will be logged in the blocks of this chain. And that's why you're charged. And that's why you should keep in mind how to develop these modules. So you always have to keep partial state changes in mind, right? You can't really rely on the module to revert your transaction if it only went halfway. So you have to build your logic in a way that will fully revert if something failed, or that will execute only when all the sanity checks have passed. That's a caveat that you have to be aware of. So this is the basic layout of a module. We'll do imports at the top. We'll define the trait, and that's just where we put our common types and so on. And then we have our macros into which we'll put the logic. This is how we declare storage. Actually, let's get into the meat of things and start developing, because we are going to run out of time otherwise. So let me just skip out of this one and fire this up. So we have here the substrate node template. I hope it's big enough to read, and this as well. Okay. So if you've gone through the prerequisite guide to set things up, you should have this up and running. The node template you can compile with the command cargo build release. And so it didn't do anything for me because I didn't do any changes. I just compiled this a while ago. Now, compiling takes a while, especially if you're starting from scratch. The good thing is that if you're only changing some files, it'll only recompile those files. So it'll actually be much faster when you make little changes. But the first compilation might take a while. It takes 10 minutes on my desktop rig. It can take up to 40 minutes on a laptop. It'll depend on your machine, but luckily you only have to do this once when dealing with a specific node. So if you go into palettes here, you will see the template subdirectory. Now, the template palette is actually the one that's included with the node template by default. This is something for you to hack on. This is here as an example. And the files that we'll be modifying are in source librs, so that's the meat of our module, and cargo.toml, which defines our dependencies, the packages that we need to pull in. But before we do that, let's check this chain out, shall we? So I'm now in the folder of this node template, and you run it by running just /target release. So every build will get put into target release, and then the binary in this case is called node template. You can run it by just doing this, but it's not going to work, because if you do this, this is not a development chain, and it's going to expect a validator. It's going to expect actually two validators. So you would have to run two nodes that connect to each other to produce blocks, and it wouldn't work. It wouldn't move. But if I do dev, it's going to run a development chain that just produces its own blocks and does its own transactions and has some unlocked accounts for you to play with. So this is great for testing your logic locally. And then when you're ready to deploy, then you just remove dev. It'll start a new chain in a new location with a new database, and you can distribute that binary to anybody you want to run your node, and then you'll have a blockchain. But for now, let's just run it with dev. You can see here that it is now working, and every time it makes a block, it'll send you all of these messages. Now, my Unicode characters are a little bit broken in this Bash emulator here, but if you're using something native like Linux or Mac OS, you will see beautiful emoticons here being output in your logs. This is just a Windows issue for me. So now the chain is running, and a substrate chain by default listens on port 9944. So let's open that up. Let's actually use our substrate frontend template. And again, if you went through the prerequisites post, you will have this folder here, substrate frontend template. And the frontend template can be started with just yarn start. So now it's starting this development server, and it's running the page for me. And this page will automatically connect to localhost 9944 so that it can read our blockchain. Connecting to substrate, there we go. So what can we see here? Let me zoom in a little bit. All right. We can see here that we have some accounts, and we can switch between them. This is the account from which we are acting. So this is the one we are logged in as. The metadata that I mentioned that's being exposed by every substrate chain can be seen with show metadata. And you can see here it's just a JSON file, and it's quite big, right? That's because it contains literally everything the chain can do. So let's try and find in this whole mess our template module. And actually let's look at what the template module contains. So in this case, it contains, like out of the box, it comes with some definitions. It comes with some, this we'll explain later. It comes with some imports. It comes with a trait definition that enables events. This is just boilerplate for enabling events. It comes with a definition for storage, so it stores something. And it comes with a definition for an event, that the event screams that something was stored. And it also has some errors here. And then there's the meat of the module. So I'm not going to go through this because we'll go through it when we'll be coding. But we have two functions in this module. One is do something, and the other is cause error. And this will just demo an error. You will see what an error looks like. So the error still changes the state of the blockchain, but it errors out for the user. And this function will just store a random, some data that you save into the chain, and you will be able to fetch it back out. So, sorry. Yeah, so actually let's demo this right away. So we have here the function called do something. Let's try and find it in our metadata. There we go. So we have a call that's do something, and that expects a unsigned integer 32-bit. So something, it expects an argument called something. And the documentation is here. So anything you write in a, whoops, wrong one. Anything you write in behind a triple slash above a function becomes its doc block, becomes its documentation. And that's why we can see this here in the metadata. The documentation is here, just a dummy entry point, blah, blah, blah. And this is how you actually add documentation to your metadata as well, so that the various UIs that connect to it can actually present it to the user. So let's try and interact with this chain. It's already on block 40 with the finalized block at 38. Pretty cool. So we have these accounts here unlocked with a bunch of coins, and we have these other accounts here that just don't really matter. These are from my Polkadot.js extension. So if you install the Polkadot.js extension, you'll be able to keep your keys in this extension. And so this will let you connect to various Web3 websites. So websites that interact with substrate-based chains, you'll be able to interact with them. Okay, let's first demonstrate a simple transfer of units. So let's demonstrate. Let's find. So Alice will be sending to Bob. Let's copy this address. Let's put it in here, Bob, and let's put 2 million. So this 1 unit is all of this because we are showing this with the smallest possible unit with planks. So we'll send 2 units over. Submit. And now it's being submitted. There we go. It passed. So transfer succeeded. And there we go. Sorry. This is our event. Balances. Transfer event happened. From account to account. How much? And there we go. And it's finalized. Wink. So we get an event when it's included in a block. And then we get another one here, notification, when that has been finalized. Of course, there's no change here because these are millions and we just sent 2 units. So nothing there. Now, we said that we have this template module, right? And the template module has some functions. And the template module has 2 functions. Do something and create error or whatever it was called. And cause error, yeah. So let's check it out. We can interact with a palette by building an extrinsic ourselves. So we find the palette that we're looking for. There we go. There's a template module. And we suddenly see, you see, it automatically offered only the functions in that module. And that's because of the metadata. So the metadata just was parsed for this. And now it offers me only these 2 functions. So let's cause an error. Now let's submit. There we go. So this extrinsic failed, that's an error, and we got a dispatch error, right? So we got the information about this error that occurred. But if we do something, let's put in 5. There we go, something stored, success, just a dummy event. So we got the event that something was stored. And now, look at this. So this UI here is a custom UI developed just for this node template as a demo. And that's for this substrate frontend template. And we'll be modifying that later for our use case. So we now have the current value here at 5. Now let me demonstrate that forkless upgrade that I was talking about. So we go to substrate node template. And now notice that our chain is still running, right? Our chain is still running. I'm not going to turn it off. And what I'm going to do now is like this. So we are going to rename this into cause an error. Insignificant change, but it's changed nonetheless. It should be visible. So now we will go to runtime of the chain itself, of the so there's this parent runtime that loads all of the palettes templates, and we need to change some information in this parent runtime. There we go. You're looking for spec version. So if you change spec version to this and then recompile, the WASM that is the result of this compilation will be different from what is running natively. And then the chain will actually grab the WASM from the chain and run that. Let's try that out. Hopefully it works. So now we've saved this. We have changed our function and we have upgraded our spec version. Now we need to recompile. So we'll open a new tab for this. There we go. And now just a typical cargo bolt release. Now notice that it only starts from like the very end. So the last 4 modules it needs to rebuild. So it's going to be fairly, quite a bit faster than it would have been starting from scratch. You can see that this 728, this means this is how many crates it has to build. So how many modules it has to build, compile, in order to get to the final one that we are using. That's a lot. So that takes a while. But in this case, it'll be done much faster because it only needs to do the ending, the final part. Okay, so while that's happening, let's also start with, we can't really start with this just yet because it's compiling, but let's try and do, okay, Well, let's go through some basics. I think it already went past the sensitive parts. Yeah, let's explain some things. All right. So at the top here, you saw this line. So this is also just copy-paste friendly. You will be copy-pasting this. You'll never be typing this out from scratch. Actually, most of this stuff you'll never be typing it out from scratch because it's all boilerplate that you can use. But it still warrants explaining. So in order to build substrate-based chains, you cannot use the Rust standard library because that's big and that would be too big to include as a WASM blob. So there's this no standard mode, and all this really means is that sorry. All this really means is that when you're not using the standard feature, then activate the no standard mode. This is just something you include in every module that you build because you want this standard Rust module mode to be disabled. Otherwise, the WASM compilation is just not going to work. It's not gonna complete. What else? This here is interesting and should be familiar from other languages. So you just import the things from substrate. So these are the code that we want to share. So this is the framework's code that we want to reuse. So we import frame support, and then from frame support we import all of these macros that we'll use. So declare module, declare story, declare event, declare error, and dispatch, which you don't actually need to import it otherwise here. From frame system, we'll also import itself because the system will let us access some system level values like the block number, for example, and a macro that lets you ensure that something is signed, right? Actually, not a macro, just a function. So whenever you submit something from outside of the chain, like the extrinsic, that has to be signed in most cases. There are some non-signed extrinsics that you can submit. That's a miscellaneous use case. But in most cases, you need a transaction to be signed. So you need it to be signed with the private key of a wallet that somebody is interacting with the chain. This function will just let you extract who the signee is if he exists. If he does not, an error will happen. So that's what this function does. It's like a shorthand convenience method for checking that a call is signed. Okay, this is done. So let's take a look if we can make this work. You can see here that we already have an upgrade runtime shortcut function. I wonder if this works. I've never used it. Let's see. So we need to find the WASM file here. All right. No template. So the WASM blob will be in target release wbuild node template runtime, and there it is, node template runtime compact WASM, and this is the file that you need to upload. So if we upgrade this, let's see what happens. So we just saw two events happen. Code was updated, that means our upgraded code was successful, and a sudo just took place. So we got an event that an admin did this. So this little module here, this little component in React that somebody built, this already applies this sudo call to our forkless runtime upgrade mode. And let's actually see if this works. Now, right now it's not gonna, but if we refresh, it should. Balance template module. Cause an error. There we go. So now our function is called differently. It has a different name, and we did all of this without even restarting our chain. The binary is still chugging along. And why is this possible? Because it just downloaded the WASM from the chain and it's running on that. And that's why the function name changed and our runtime upgrade was successful. We didn't brick the chain. We didn't need to hard fork. We didn't even need to upgrade our built binary. We didn't need to do anything, and it just worked. So if we wanted to do this manually, like without this shorthand convenience component, we could do this through the palette interactor as well. So we could pick the sudo, and we could pick sudo unchecked wait. So this unchecked wait function is what you would call when you're doing the forkless update. It's slightly more complex. This is why it's abstracted here in this part. And then you have the call, which needs to be encoded, and then you need to add the weight, which you expect. So weight is like if you're familiar with gas in Ethereum, that limits how many calls can fit in a block. This is weight here. So weight is let me show you in code. You can see above a method here, weight equals 10,000. So there's a limit of weight per block, and like any function call that exceeds that limit is not going to make it into that block. It'll be queued up for the next one. So it's very similar to gas. I should note that this only takes into account the time to execute the function. So this is CPU time. Weights are based on CPU time and the cycles that it consumes, but it's not based on transaction size, so it doesn't take into account state growth and stuff like that. So this is just computationally how much it costs to execute a block. And there are some benchmark tools that you can use when you're building your own palette, how to benchmark your functions to be in line with the weight that we expect. You need to be within a certain limit, or otherwise you are going to have trouble including your transactions. And also, some processing might be so heavy that your validators will start lagging behind, right? So if you leave unchecked weight, then you might apply too much for the validator to process quickly if there's too many heavy function calls. And this can interfere with block production. So this is why the weight system is there, to limit this whole CPU processing per block to a reasonable number. Anyway, I can't really fill this out off the top of my head, so I can't demonstrate this. But then what would happen is, when we fill this out with some data, I don't know, whatever, we would click sudo, right? And then sudo would execute the sudo module. So only the sudo command will invoke the sudo powers of our Alice account. Alice is the sudo. When you run the dev chain, Alice is the sudo account. The sudo button would invoke the Alice sudo powers to call this combination of extrinsics and produce the same result as this upgrade runtime thing did for us. Now let me show you something else. Actually, we are kind of running out of time, so let's go into building the custom thing. Let's delete everything from lib.rs. And don't worry, I'm going to share a written version of this tutorial after the workshop with you, so you can follow along with this at your own pace. You don't have to rush along with it. Let's check it out. So like I said, you will first have to import some things, right? So we have here the configuration flag for no standard, and that's just always has to be there. Then we are importing some macros, and here I have changed it to include also the ensure macro. And the ensure macro just is like an assert. It's like make sure what we put into parentheses is true or emit an error. And we need the storage map to store some values into our chain. Now, what we're going to be building here is a proof of existence blockchain. A proof of existence blockchain lets you log the existence of a file or some data at a certain point in time and make it cryptographically verifiable. So if you have like a song and then somebody comes out and says, no, this is my song actually, then if you registered it on the proof of existence blockchain, you can actually prove that you registered it at a certain point in time. That's the point of these. It's like a blockchain notary, right? So we'll do that. So for that, we will need to kickstart our module. And I said that we need to define the trait. And inside the trait, we put this type event. So if you don't, this is again boilerplate code. If you don't put this, your module can't emit events. That's it. And then we have these macros with their fake bodies here that we will be filling out. Let's first put this in. So the module is defined through a struct. So you define this pub struct. Again, this is all, you're going to be just pasting this in. But what matters is that this origin thing. Whenever you're building your custom palette, your custom blockchain, the very first argument of every single function inside of that module will be origin, always. And origin is where that transaction is coming from. And that's what we will be ensuring is signed. So origin is the origin of the transaction, and it's always the first argument of every function. Now, to activate these basic metadata sharing functions of our chain, we need to include these two lines as well. So we need to declare a type of error, and we need to set the function of deposit event to be default. Again, boilerplate code, you would be including all of this every time. This just makes it possible for the module to emit errors and events at all. Otherwise, it can't do it. Now, we will need to, because we're storing strings into our blockchain, and I mean, we're storing hashes, and hashes are just strings. We will hash a file, and we'll store it hash, and then we will register that on the blockchain. So a hash is just a string, and since we're storing strings, strings in Rust are represented as vectors of bytes. So we will need a vector structure to use so that we can store vectors. So we'll import that, and we'll import that from the standard palette. We'll import vectors, but we can't just import that without actually adding the dependency in as well. So this is where we will be modifying our cargo toml file. Sorry. Yeah. So let's modify this cargo toml. Let's put it at the bottom here. Okay, and then we will add this. So we have sp std /std. So now we have this standard library loaded in, and it should work. We can add a comma here. So now we have this dependency. When we build, it'll pull this in. It'll build it for our module. We now have access to our vector, right? So let's now define some events. We said that we wanted to register our file on the blockchain, so there are two events that we could fire. We could fire that if I'm registering a file, I'm registering a claim for that file, so I'm claiming that it's mine, that I registered it. So we can call this claim created and claim revoked. It's very straightforward. So this is how we do events. You have an enumeration, so a list of events where this account ID will become available to us from this trait through the account ID type. And the / above events is again the event description, the event documentation. So when an event is emitted, it will have this description inside it available for reading by any client that connects to it. Again, helping the UIs and helping the wallets build things. So we have two events. One is claim created, and that will emit account ID and a vector of bytes, which will be our hash. And claim revoked will emit the same thing. So anybody listening in can just read this. A caveat here that trips a lot of people up is that event enums and enums in general in these macros, because these macros are not pure Rust code, they're macros. They have some caveats that are designed to minimize shooting yourself in the foot. But sometimes it trips people up. One of those trips is the ending comma, the trailing comma on the enum list. It has to be there. Otherwise, it's not going to even let you compile. So these enums need a trailing comma at the end. Then, so now we have these. These events for claims, right? Now, what kind of error can we encounter in our palette? Well, somebody may have registered this claim before. The claim may not exist if we're trying to delete it, for example, if we're trying to revoke it, or you can try to delete a claim and not own it, right? We don't want anybody to delete anybody's claim. So let's put that in as well. Again, an enum, a list of errors, and messages for those errors are here. Okay. Finally, let's declare the storage, and I'm going to speed up here because I'm running out of time. This is how this works. So you define a trait store for module T, and this part here is important. This is what defines the prefix in the database. And whenever you're building a pallet, this has to be reasonably unique among other pallets in your blockchain. Because if they share this, they will share a prefix in the database. This is going to get hashed as a prefix, and the data is going to get appended to it. So if I name this foo and somebody else names it foo, names their storage item foo, then our data will clash, and that's not good. So make this as unique as you can every time. No need to do random numbers or something, but if you just call it like your pallet, should be enough if people are mindful to look into what kind of pallets they're including in their chains. This is the name of our storage map, and that's going to be a map of hashes, and these hashes are going to be hashed by Blake 2-128 concat hashing algorithm. This is the default, but it has to be verbose. You have to express it like this. Again, very copy-pastable. And these hashes will map to tuples of account ID and block number. So we're going to store account ID and block number for every hash that we include. And these hashes are going to be those file hashes. Finally, let's build those functions for our module. I'm just going to paste this in because we are very much out of time. So we now have these functions in here. So we have a create claim function and we have a revoke claim function. Let me just put this into build mode so that we can maybe attempt to run it, but let me explain it while it's building. So we define a struct for this module. This is again a copy-pastable template. You will be using that. These are the template functions that we included before. Now, these are the individual functions, and you can see that they're heavily documented. This is from that tutorial that I'm going to share with you. So the create claim function is going to do the following. It contains, like I said, the first argument is always the origin, and the second one is the proof, the hash of the file that we're trying to save. So first we'll grab the sender by ensuring that the origin is signed. This here, the question mark, means either return the origin, either return the sender or error. So this just is a one line for give me the sender of this transaction or error out. Then we'll make sure that the proofs storage map does not contain this proof that we're trying to save. If it does, we emit the error that the proof is already claimed. Somebody already submitted it. Then we store the current block from the system module. We grab the block number and we insert this proof into our storage map. You may be wondering why this ampersand here. This is because of a Rust mechanic called borrowing. In Rust, if you send a variable into a function without borrowing, then that variable stops existing inside the context where it was sent from. So we would be unable to use proof if we didn't use this ampersand here, because it would disappear from our context here. But the ampersand means do what you need with this and then send it back. So this is why this happens. And this is why we don't need them here, because we'll no longer use them in the function. This is where the garbage collector can discard them. And so we save this into the blockchain, and then we emit the event that the claim was successfully created. So the revert function does a similar thing, but in reverse. It also checks if the sender is the owner, which we'll go through if we have time. Let me see how this is working. Okay, it's still compiling. So we have here the sender. Again, we grab the sender. We then ensure that proofs exist, that this proof that we're trying to delete exists. And if it doesn't, then we emit an error, no such proof. Then we get the owner of the claim. So we take our proofs storage map and we get. Get is a built-in function in our storage map. So no need to specially define it here in declare storage. This is built in. So we get our proof out of this. But since we are binding our hash to a tuple, so two values, account ID and block number, we would get that tuple here. So the way we extract the owner is we say let and then like this. The first variable that we extract from this tuple will be applied to the owner variable and everything else will be discarded. This means discard. So it will just grab the account ID stored here. It'll just discard this. We don't care about the block number. And then we ensure that the sender is actually the owner. So we equalize these two. And if not, then we emit an error and we stop the execution. Again, if we stop here, the state of the chain changed so far, and we have to charge the user a fee. So this is still going to cost them some money if they failed. Then we remove the proof from our map, and then we emit the claim revoked event. Okay, let's try and test this out. Hopefully, there we go, it compiled. Now, since I failed to increment the spec version, this wouldn't work as a forkless upgrade. So let's rerun the chain. In this case, we're going to stop the chain and rerun the binary. Now let's try this out. Hopefully this works without purging the chain, but even if we purge it, it's not a big deal. Let's interact with the palette. You can see here that our template palette is, the component is gone. So something is different. Let's see, template module. And we have here create claim and revoke claim. So now if I put in here the bytes, let's say this is obviously not a good file hash, but we'll just put that in. Let's sign it. And we have just created a claim for this file. So we have just claimed this hash. Now let's try to claim this from the Bob account. The same thing, signed, let's see. Failed. All right, so we have failed this claiming because this proof is already claimed. Let's try and revoke this claim from the Bob account. Again, failed, doesn't work. But if we try to revoke this from Alice, there we go, we revoked the claim. So now we have deleted this claim. That's basically it. So this is how easy it is. You know, you can see in like, there we go, under 100 lines of code, including comments, we just built a custom palette for our blockchain that allows you to do some very application-specific stuff. And this blockchain can be connected to the Polkadot ecosystem to share the security with all the other blockchains. So this is how we are building the huge ecosystem that is going to be Polkadot. And this is how we're going to connect to the other chains by building functionality that makes it very easy to get started, very easy to get very specific with your logic, and still not deviate from the very practical shortcuts that we've built into Substrate itself, like the metadata sharing, like the forkless upgrades, like the UI compatibility, and so on and so forth. Thank you for listening. If you're interested in this, if you want to check out more content, if you want to check out more tutorials, please go to substrate.dev and go to tutorials there. Including this tutorial, there's a bunch of others there that you can try out, setting up your own private blockchain, building visualizations, stuff like that. Go there, dive in, and I hope you'll have fun because this is designed to be fun and easy and approachable. And I hope to see you in the Polkadot ecosystem. Thank you very much.